As we've seen, the functions of s in the frequency domain are rational functions with polynomials in both the numerator and the denominator. We can take and factor the numerator and denominator polynomials into their factored forms so that the numerator then can be written as s plus some z1 times s plus z2 times s plus z3, where these values of z are known as the zeros of the function because they represent the values of s that cause this. For example, negative z1 represents the value of s that would cause this factor to equal 0, which makes the function itself go to 0. Similarly, negative z2 and negative z3 would be the factor or the values of s that would cause the function to go to 0, thus those values are referred to as the zeros of the function. Similarly, in the denominator, negative p1, negative p2, and negative p3 are referred to as the values of s, or are referred to as poles, because they are the values of s that make the denominator function go to 0. And of course, when the denominator goes to 0, the function itself is undefined. Or the asymptotes of the function are known as poles. So for example, here we've got a function f of s that has one 0 at s equals positive 3, because when s equals positive 3, this function, or the numerator, goes to 0 and the function goes to 0. On the other hand, we have 1, 2, 3 factors in the denominator, and we have poles at s equals minus 8, s equals minus 3 plus j4, and s equals minus 3 minus j4. And of course, poles come as complex poles come as complex conjugates when we've got real coefficients in our polynomials. So we can take this function here and plot it in the s plane. Because s is a complex value, it has both a real part and an imaginary part. And so in this this complex plane for s, we have a 0 which we denote with a circle at s equals positive 3. We have one pole which we denote with x's at s equals negative 8, and then the pair of conjugates at s equals minus 6 plus j8 and s equals minus 6 minus j8. Now, where does this terminology poles and zeros come from? Well, zeros are pretty obvious. They're the values of s that make the function equal 0. But why do we call it a pole? Well, to understand that, let's look at the graph of f of s. Now, because s is a two-valued function, it takes a third dimension to represent f of s. And in fact, there's both a magnitude of f of s and there's a phase of f of s. So let's look at the magnitude of f of s in a three-dimensional plot. Okay, so here's our function mapping the real part of s along this axis, the imaginary part of s along this axis, and then the third dimension coming on up here representing the magnitude of f of s. So what we have is a surface here with a 0 over here at x equals positive 3. And then we have these poles, places where the magnitude of f of s goes to infinity. Well, in a three-dimensional plot like this, they represent points in a surface that go to infinity. It's as though you had taken tent poles and place them up underneath this surface at the points where the poles of the function exist. Thus the name pole, or the name for poles. And you can see that this one exists on the real axis, a single pole. These two exist off of the real axis and come in complex conjugate pairs.